So today we are going to continue with chapter 2. We're going to cover lesson 7 today. It's going to be function operations and composition of functions. So the operations that I'm referring to are finding the sum of two functions, the difference, the product, and also the quotient. Notice the only one that has an exclusion would be the quotient, where the denominator can't be 0. So that's the only exclusion we have, is when we're trying to divide the two functions. Now, notice by definition, it's just stating that you take the f of x function and then you're going to add it to the g of x to get the sum. Do the same thing for subtraction. You would just take the two functions and subtract them. And then for the product, multiply them. And for the quotient, you would divide them. For the example I'm going to show you now, all we're basically doing is just putting the two functions together and then putting the appropriate sign in between them. So for our first example, and we're going to talk about the domain of these functions in a minute, but first let's go ahead and perform the indicated operation. So notice my indicated operation for question number A, or part A, is to find the sum. So all I'm going to do is, by definition, what this states is f of x plus g of x. This is how you can write it. And then now I'm going to take what f of x equals and put it right here. And then I'm going to take what g of x equals and put it right here. And I'm done. So if it says to find the sum, and there are no like terms to combine after you put them in there, then you just leave it. I cannot add 8x to that radical or the negative 9. So I would just leave it just like that. I'm going to do the same thing on the subtraction of the two functions. Again, by definition, it's the f of x function minus the g of x. So 8x minus 9, and then I'm going to subtract the g of x function, and I'm done. The difference, when it's a subtraction sign. Here I'm going to find the product. Again, by definition. So by definition, this means the f of x function multiplied with the g of x function. And again, I'm just going to put them in parentheses. I do not have to multiply anything here, because I'm not going to multiply something outside a radical with an inside. So I'm done. When we're finding the domain of two functions that we've either added or subtracted or multiplied or even divided, their domain is going to be the intersection of the two functions. Now, notice in this particular example, my f of x function, remember when you're finding the domain of a function, you're always starting out by assuming it's all real numbers. The only time we start excluding things is when we have a fraction or when we have a radical. So notice in my f of x function, there's no fraction, there's no radicals, so I can already see that the domain of the f of x is all real numbers. The same thing for the g of x. I'm going to start out by assuming it's all real numbers. However, wait, red flag, it's got a radical. So remember, when it's just a radical, you take what's underneath it, and it has to be greater than or equal to 0. So then I would solve for x, and I can see that my domain here is going to be all of the x values that are greater than 1/2. So the domain for the g of x function is actually going to be 1/2 with a bracket to infinity. So the domain for this is the intersection between the f of x function and the g of x function, its domain. So the domain here is everything greater than or equal to 1/2. Clue that you could use for domain is in the lesson 2.5, where I showed you all of those parent functions. Remember, the identity or the linear was always all real numbers. The x squared function or the parabola was always all real numbers. The absolute value function is all real numbers. The cube function was all real numbers. So if you remember from 2.5 that it's always all real numbers unless it's a fraction or unless it's under a radical. Then that's where we may have some exclusions. So let's try the example D. So far we've added, subtracted, and multiplied. Now we're going to apply the quotient, or we're going to try to divide these functions. So again, by definition, it's f of x divided by g of x. And again, I'm going to just write my f of x function on the top and my g of x function in the denominator. And again, that's how you would leave it. However, let's try to find the domain of this thing. So again, the domain of the f of x function, remember, was all real numbers. The domain of the g of x function was, remember, it was everything greater than or equal to 1/2. Now, when we're doing this, we now have to check out the domain of our simplified or our quotient here. So now, for this one, the numerator is still all real numbers. However, this time the denominator has to only be greater than 0. Remember, when there's a radical in the bottom, you only use the greater than 0 because it can't be the greater than or equal to, because it can't equal 0. So for this one, we're going to solve this, and the only difference is instead of a bracket, it's now going to be a parentheses because it cannot include 1/2. So for the domain for this one, when I go to graph this, remember the f of x function is the all real numbers. The g of x function, if I put the 1/2 here, it's a closed circle. And then lastly, the simplified quotient domain is an open circle. And it's going this way. So now, it has to be an intersection of all three. So my answer here for the domain for part D is actually everything that's greater than 1/2. It cannot include 1/2 because it'll make my denominator 0. So this time I'll exclude it, yes. Next example, new f of x and new g of x. But again, this time, instead of just combining them, I'm actually finding the value of x. So what I'm going to do here is I'm going to find the value of f of 2 and g of 2. Once I plug in 2 to each of the functions and get my answers, then I'm going to add them. So first I could do f of 2. I could do it right above here so I can see my function. So I'm going to do 2 squared minus 1, 4 minus 1, and my f of 2, when I plug in 2 to the f function, I get 3. And then for the g of x function, I'm going to plug in 2, and 2 times 2 plus 1, 4 plus 1, and g of 2 equals 5. So now that I have what f of 2 equals and g of 2 equals, I can see that f plus g when x is 2 equals 8. Now when I go to do part B, I'm just doing f of 2 minus g of 2. Well, I've already found out what f of 2 and g of 2 are, so I just have to put the numbers I just got, but now instead of adding them, I'm going to subtract them. So f minus g, when I plug in x equals 2, gives me negative 2. So the next slide has the composition of functions, and this is just what it's defined as. Now, notice this little symbol here. It looks almost like a multiplication, like a little dot, but notice this is actually an open circle. So, and this is read as the composition of functions f and g. But this one would be read as the composition of functions g and f. So the order of the letters is important. So when on our first example here, or our first definition, what we're going to do is we're going to plug the g function into the f function. And then for this one, whatever the second letter is, that's what we're plugging in to the g function. We're going to see some of these in action here. So here is our first example. Again, we have two functions, an f of x function and a g of x function. So the first example wants us to find the composition of function g and f and g. So here I'm going to take f and I'm going to take g and I'm plugging that in. But notice this time they told me what x equals. So really what I'm solving is f, and then I'm going to put g of 2 inside here. I'm going to work from the inside out. So what I'm going to evaluate first, or find the value of, is what g of 2 equals. So I'm going to come over here to my g of x function, and I'm going to plug in 2 for x. 4 over 1. So my g of 2 function equals 4. So the value of g of 2 equals 4. And now the value of g of 2 actually becomes the x that I now plug in to the f function. So now I'm going to take my f of x function, this one, and where I see x, I'm going to plug in 4. So now 2 times 4 minus 1 gives me 8 minus 1, which gives me 7. So f of 4 equals 7, which is really the answer to the original problem. So the composite function of f and g when x equals 2 is 7. Everybody with me on that? Let's try another example. Now we're going to flip the letters, and we're going to take the f of x function and plug it into the g of x function, but this time we're going to make x equal negative 3. So again, same two functions. So here, I'm going to rewrite this as g of f of negative 3. I'm going to first work on the inside. So I'm going to take my f of x function, and I'm plugging in negative 3. So f of negative 3 is equal to 2 times negative 3 minus 1. Negative 6 minus 1. And f of negative 3 equals negative 7. So now instead of writing this, g of f of negative 3, instead I'm finding g of negative 7, because f of negative 3 equals negative 7. Now I'm going to take my g of x function, which is the 4 over x minus 1, and I'm going to replace negative 7. And I get 4 over negative 8, which will simplify to negative 1/2. So so the composite or composition of g and f when x equals negative 3 is negative 1/2. So the domain of the f of x, again, is all real numbers. The domain of the g of x function, we start out as all real numbers, but remember it's a fraction, so we set the denominator not equal to 0. So we will exclude 1 from our domain. Now, let's go ahead. We've found them separately, the domains. So now, again, we also have to take into consideration the composition. So again, we're going to take the g of x function, and we're going to plug in the f of x function. So my g of x function, again, was 4 over x minus 1. So I'm going to take out this x, and in place of it, I'm putting 2x minus 1. So 2x minus 1 goes in place of x, and then I still had the minus 1. So now I'm going to simplify that, and I get 2x minus 2. I now can reduce this and divide all three numbers by 2, and my simplified composite function is 2 over x minus 1. Now, in addition to intersecting the domain of f of x and g of x, I also have to make sure that nothing else needs to be excluded from this one. But notice it's going to be the same exclusions as my g of x function. Everybody with me on that? So if I set x minus 1 again not equal to 0, I get the same thing that I got right here. So when I go to intersect the three domains, my f of x function, remember, was all real numbers. My g of x function is going to be everything except 1. So everything here, and then the same thing for my composite function. It's going to be everything. So the intersection of all three is really just the g of x domain. So negative infinity to 1, union with 1 to infinity. So this will be the domain of the composite function. So we're going to take our g of x function, and in place of x, I'm putting f of x. So my g of x function is here. I'm going to take out x squared and the x, and I'm replacing it with this. I'm actually going to square the 4x plus 1. So I'm going to put 2 parentheses 4x plus 1 in place of the x squared, then 5, and then 4x plus 1. I now need to simplify this. So I'm going to FOIL it, and I get 16x squared plus 8x plus 1. Here I'm going to distribute the 5, and now I'll distribute the 2. So 32x squared plus 16x plus 2. I'm dropping down the 20x and the plus 5. I now need to group my like terms. So I have two x's that are like terms that I can group. Nothing to group with the x squared. And then I can group the two constants. So this will be my simplified composite function. Notice the domain of the original ones of my f of x function. It's linear, so it's all real numbers. Notice the second function, the g of x, no fractions, no radicals. It's a parabola. And if you remember from lesson 2.5, all squared functions are also all real numbers. And notice my answer here, my simplified composite function, is also a quadratic equation or an x squared function. So the domain of this one is all real numbers. We're going to find the composite function of f and g. So again, we're going to take the f of x function, and we're going to plug in the g of x function. So essentially what we're finding is f of 2x squared plus 5x. So we're going to take the f of x function, 4, take out x, put in 2x squared plus 5x, and then plus 1. Because remember, your f of x function was 4x plus 1, and your g of x function is 2x squared plus 5x. So I'm taking my f of x function, taking this out, and putting this in there. I'm going to distribute the 4. And notice once I do that, there are no more like terms. So again, no fractions here, no radicals. Again, the domain will be all real numbers. Okay, another composite. This time we're changing up our f of x and our g of x. Again, the process is still the same. I'm going to take my f of x function, and in place of x, I'm putting my whole g of x function. So here is my f of x function. I'm taking out x, and in its place, I'm putting that. So this will simplify to 1 over, instead of now 1 over x, it's now 1 over the square root of 3 minus x. So let's go ahead and try to find the domain of this one. So first, let's find the domain of the f of x. So remember, normally we start out thinking all real numbers until we stop and see a fraction. So as soon as I see it's a fraction, I know my denominator here, x cannot be 0. So my domain for this one is going to be x is not equal to 0. I want negative infinity up to 0, union with 0 to infinity. So that would be the domain of the f of x function. Now I need to find the domain of the g of x function. Again, notice the g of x function isn't a fraction, but it's a radical. So for here, I'm going to take what's under the radical, and remember it needs to be greater than or equal to 0. So I'll solve that. So 3 has to be greater than x. If you want to flip it around, we get that. So that is the domain for...
Wait, if it's in the denominator, why is it already equal to?
Well, I'm only doing the g of x right now. But in a minute, I'm going to do it with just greater than. So for here, it's going to be negative infinity to 3, bracket. Now, that's them separately. Now I'm going to do the simplified one. And this is what Ceci just said, that it can't be equal to 0. So we're just going to make it greater than 0. Make sense? So we're going to add x. And we get 3 has to be greater than x, or x is less than 3. And again, remember, it's an intersection of all of them. So for here, if I go ahead and test this out, so the f of x is just a hole on 0. And then the g of x, this had a bracket on 3, or a closed circle. But then this one was an open circle. So for this domain, again, it's going to be where all 3 are in common. So it's going to be from negative infinity up to the 0, union with 0 to 3. And we're not going to include the 3 because that would make the denominator 0. One more example. Okay, same functions. So we're going to use f of x 1 over x, and our g of x is going to be the square root of 3 minus x. This time they want us to find the composite of g and f. So now I'm going to take g and plug in f of x. So where I see x under the radical here, I'm going to put this. So this will become 3 minus 1 over x, all under the radical. So I've taken this function and I took out the x and I put in that. So now I need to find a common denominator because I need to simplify this thing. So my common denominator is going to be x. So I get 3x over x minus 1 over x, because whatever you do to the bottom to make it have an x, you do to the top. So now I'm going to simplify this and just show it as 3x minus 1 over x under the radical. Now, remember, what's under a radical can never be negative. So I'm actually going to set this up similar to what we did at the end of chapter 1. Remember those rational inequalities? So this is what I need to solve. So my radical here cannot be less than, it has to be greater than or equal to 0. And remember, when you solved rational inequalities, this is where you set the numerator equal to 0 and the denominator, or what it shouldn't be. A lot of you on the test did the denominator only, and it messed up your interval notation. So when I go to solve this, 3x not equal to 1, and then here, so my intervals, or the breakup of this thing, I'm going to do that number line with the check marks now. This is going back to chapter 1. So I make my intervals here with a 0 and a 1/3. I'm using this inequality, 3x minus 1 over x has to be greater than or equal to 0. So I need to pick a test point. I cannot choose 0 because it was one of my answers. So I'm going to use 1. I'm going to plug it in. So 3 times 1 minus 1 over 1. I need to see if that's going to be greater than or equal to 0. 3 minus 1 over 1 gives me 2, and that is true. So check, x, check. So now here we can see that our interval for this answer is going to be from negative infinity up to 0, union with 1/3 to infinity. So this is combining what we did at the end of chapter 1 into this problem, because we had a fraction under the radical. So your homework tonight is 9 problems. 27, 29, 49, 51, 53, 57, 59, 61, 63. So you have time now that you can get started on it. And then tomorrow I will work out any of these that you need to see or any of the graphing questions.